So we have this prescriptive design methods like the code methods or the performance-based design methods. Main difference in here, we're going to have design equations. With these design equations, we should be able to find out the design forces on the structure. Take these design forces, apply them on the structure itself and the structure members, come up with a design, compare phi m to m sub u, phi p and p sub u, and also phi v and v sub u. So it's going to be like a strength space. In the performance space, the story is going to be completely different. You're going to come here with your first estimate with the member size, apply the dynamic analysis to it, find out the deformation, which means displacement of the structure, come up with lateral force displacement curve, which means the performance curve of the structure members, and find out what would happen at this displacement demand, if you like, and find out the strains and the stresses in all the structure members. If the strains and the stresses are within your limits, your design is good. So with this design here, it gives you more chance to control your design and change the members the way you want it. In many cases, you have a building that you design with the prescriptive design method, which means with the code, and you really need large members to be able to resist the design forces based on the code values. If you take the same structure here and apply the performance-based design method, you're going to see most likely it's going to be okay. If here the margin and difference in the code method was not really high. So I'd say, as a rule of thumb, if you are off here by 10%, you should be fine if you do performance-based design. This is going to be kind of guaranteed. Now the code allows you here to use both of these two methods. But this method is going to be kind of expensive to perform. And in many cases, difference in design wouldn't be that big. If you have kind of a regular building, certainly you're going to go with a performance-based design. You don't want to go with the prescriptive design method. You don't want to use the code equations. We went through this table last time for the method that you're going to be able to use. And as you see here in this matrix, everything is going to be permitted except for this type of analysis, the static. And with this static design force or equivalent lateral force procedure, equivalent means is going to be static force design, meaning that you are going to come up here with some design forces going to be equivalent to the dynamic design forces. But this is going to be here static. As you see here, is going to be equal to seismic coefficient multiplied by the seismic weight. Like what we said last time, seismic weight is going to be mainly the self weight of the structure. Plus, if you have a storage occupancy, it's going to be 25% of that. If you have an office or some residential building, you are going to have at least 10 PSF for the partitions. If you have any permanent equipment, generators, air conditioner units, you need to include all of that. If you have, let's say, elevator equipment machine, room, it has some equipment, also need to include the weight of it. And if you have some snow load with PF, which means a full load of the snow, more than 30 pounds per square foot, you take 20% of that. The design equations, this is going to be like the famous design static or lateral force, equivalent lateral force procedure. And they're going to be all based on the code response spectrum. And as you see here, when natural period of the structure is going to be going up, we discussed this also last time, when this goes up, seismic design force is going to get reduced. This is the reason that the code, when it comes to natural period, it gives you a limit, like a maximum value. Otherwise, you can't really use this natural period of the code. The risk category, as we said, that we have 4 risk categories. And most likely, if you have an office or residential, most of the building that you see around you is getting this category 2. Category 3 is going to be essential buildings. And category 4 is going to be emergency buildings. Based on the risk category, we're going to come up with this I sub E, the seismic importance factor. As long as you are 1 or 2, your factor is going to be 1. Once you go here to risk category 3 or 4, you see here the factor you're going to be designing for 25% more or 50% more seismic forces. So where is this I sub E comes into the picture? I'm going to go back here and look at my equations. When you look at it, it says CS is going to be equal to SDS and then R divided by IE, the seismic importance factor, meaning seismic importance factor is going to be actually a multiplier times SDS in all the equations.
Professor, would high-rise buildings be risk category 4?
What's that?
High-rise buildings?
It depends on, it is going to be 3, but depends on the number of people that you can fit in there.
Okay.
Yeah. So if you look here at this one here, any other occupancy with occupant load greater than 5,000, this is the reason that if you have a high-rise building, most likely it's going to be one of these. But if you have a high-rise building, why would you do code analysis for it? If you have high-rise building, absolutely it's going to be performance-based. You cannot really make a high-rise building work. I mean, you cannot make it work if you're doing here this this code design analysis. You can't use this equation. I mean, the size of course is going to be really large, and it's going to be very tough to make it work.
Right.
With performance-based design, you'll be able to make it work.
Performance-based design. Okay.
Now, when it comes to natural period here, we have the approximate method, and as you see here, we went through this also last time. We said it's going to be equal to some factor, some coefficient times the height of the structure to the power of x, and here's the x value and CT value. And as it says here, if you have a steel mount frame, your CT and x is going to be this much, right? Concrete mount frame is given to you. Eccentric brace steel frame, here we go. Steel buckling restrained brace frame. This is like brace frame, special brace frame, and they put it the same as eccentric brace frame. All other structure systems is going to be 0.02 and 0.05. So this is simple here. You can just have the C sub T and X. You understand what type of structure you just applied in this equation here. Code says, if you like to use this equation and use this natural period, this is going to be okay. There is nothing wrong with that. But this value is going to be kind of a small value, and you don't want to use it. You'd like to go to a larger value. So most likely you're going to be doing dynamic analysis if you have a structural steel building. So my discussion here is going to be kind of specific to structural steel buildings, and it's going to be multi-story. I'm not talking about a wood structure, small building. I just say, just go ahead and use this because you don't have means or methods to determine kind of the accurate natural period. So in a case like this, most likely you're going to be using dynamic analysis to find out the accurate natural period. And once you have it, you need to compare it with this natural period, with the approximate method. And when you compare it, you don't just compare it with T sub A, you compare it with C sub U times TA. So the maximum natural period that you're going to be able to use is going to be equal to C sub U times TA. So after you determine this, right, then now you figure out a natural period, accurate natural period or exact natural period of the building based on dynamic properties of the structure. You compare it against C sub U times TA. So C sub U is going to be a new factor. And if you like, it's going to be based on, you can look at here, it's going to be based on SD1, the factor SD1. Or you can just look at this chart. I don't think that this chart in the code, I just made up this chart, is going to be based on SD1 versus C sub U. And as you see here, the lowest value for SD1 is going to be equal to 1.4. So at least it's going to be equal to 1.4. You have here 40% above TA, right? To be able to use T accurate. If your SD1 is going to be real short, like 0.1, unless it's going to be 1.7. In between, you can do this interpolation. So what does it mean by accurate? Again, accurate design methods or accurate methods of calculating the natural period. I'm going to give you here a couple of equations. The first one, this is what we have seen before. This one is going to be for single degree freedom system. And this one is going to be for multi-degree freedom system. I'm not going to say if you have real multi-degree freedom system that you're going to be able to use this. If you have a real building that you really would like to do, it means that you need dynamic model. So you have one of the software, you have maybe ETABS, you have SAB, you have RAM structure system, one of the softwares that you should be able to use, right, to find out the natural period, the exact one. So these two equations is going to be good for hand analysis. So it is good for our business here. But if you're going to put your building here in a structural model, you don't really need to look at these equations. So I'm going to say here, we have here 3 methods of determining the natural period accurately. The first 2 equations, the first one for single degree freedom system, the second one multi-degree freedom system, and the third one, if you can build a computer model and just let it do the job for you. And in a case like this, you're going to have lots of natural periods. Now the R factor that goes into my equations when it comes to the code design equations, it's going to be based on the type of structure, the type of building. We have something called here called bearing wall system. In a bearing wall system, most of the gravity load is going to be supported by walls. So, okay, what type of walls do we have? I'm going to be looking here at all the walls that I can use when it comes to structural steel. Do you guys see the structural steel in here? Yes? No?
No.
So we don't have it here? We don't, right?
Correct.
Okay. Anything here? Still under this, the same one. Light frame, light frame, light frame. We don't have it here.
There's light frame or steel sheets.
This is sheet panels. Like, do you know the name of it?
No.
Okay, this is just like wood frame. Most likely it's gonna be metal stud, and then they bring sheets and you attach to it. You can also use it with wood. It has higher trends than plywood, but this is not the one I'm talking about. As you see here, it says cold formed steel, right? Cold formed steel, strap bracing. So this is not the one that I'm talking about. We have another system here, which is called building frame system. What's the building frame system? If you remember last time, we discussed mount frame system or mount frame building and building frame system. In a building frame system, you don't have mount frames. You can have brace frame, concentric brace frame, or eccentric brace frame. Look at the R factors here for the eccentric brace frame. It's going to be 8. The special concentric brace frame, right? This is going to be the special. It's going to be R factor of 6. So if this concentric, it's going to be 6. Eccentric is going to be 8. So the one that has a linked beam, it has higher ductility. How could I compare here the ductility? By just looking at the R factor. So the concentric brace frame is going to have lower value, which means it's going to be less ductile than eccentric brace frame. Look at the ordinary concentric brace frame, 3 1/4 compared to the 6. So what is the big difference between the two? You can say, well, the difference is going to be in detailing, in design of certain structural members. And we're going to see this when it comes to mount frames. I look here for this omega naught, which is over strength. I don't really need to address it now. Deflection factor or amplification factor, which is kind of the same thing that we have discussed about ductility factor. And then based on the side design category, it says here the height limit. This 160, and this gonna be no limit. NL no limit, 160 feet, 160 feet, 35 feet, right? No limit. NP means not permitted. You cannot really do it. Look at this. Steel and concrete composite ordinary shear walls. steel and concrete composite special shear walls. So here we go. This gave you the steel shear wall that we were talking about. And look at the factors, gave you 6. Steel and concrete composite plate shear wall, 6.5. So it is here, but they don't put it in the bearing wall system. It is actually part of the bearing frame system. Because in a case like this, you're not gonna let this steel shear walls to support your gravity loads, most of the gravity loads. But most likely you're gonna have columns to support most of the gravity loads. I'm gonna come here to the next category, which is our category here, the moment resistant frame. Now, once you have your moment resistant frame, I'm gonna start with the steel special moment frame and look here at the R factors, give you 8. And then you have different R factors. You can go to ordinary, and then you have also, you can see also intermediate, 4.5. Look at the big difference. The one that we'd like to use is gonna be this, the special moment frame. This is the one that has the RBS connection or have the top plate. So as long as you're able to control the plastic hinge location, you can take this R of 8, besides lots of other consideration when it comes to steel design of members. Now, so which one is more ductile? Is it the special moment frame or the concentric brace frame? I simply here can look at this. It says here special moment frame, R factor of 8. Concentric brace frame also is going to be special, is going to be 6. So the moment frame is going to be more ductile. So, okay. Now we have a dual system. This one you combine a stiff member with a flexible member. A stiff member is going to be like brace frame, whether it's going to be concentric or eccentric, you put it to the moment frame. So let's see, read here what it says. It says dual system with a special moment frame. So number one, if you like to go with this dual system, you need to have a special moment frame. This is going to be category D. So it has to be a special moment frame. It cannot be the intermediate moment frame. It needs to be a special moment frame to be within this category D. Now you put this moment frame, which is capable of resisting at least 25% of the prescribed seismic forces. So the problem is when you put a brace frame with a moment frame, the brace frame is going to be taking maybe 90% of the load, maybe 95%. So as we say, usually it sucks all the load, lateral forces. Why? Because it is stiffer. When you have a stiffer member and you put a vertical load to it or horizontal load to it, the stiffer of the two members is going to be sucking most of the load. So if you put here a moment frame, you put in the same direction with a brace frame, the brace frame is going to be taking maybe 90% of the load. So in a case like this, the moment frame is going to be designed only for 10%. So what the code says here, this is not good, this is unfair. Because what you're doing, you're just adding a very flimsy moment frame, and this moment frame is going to be very weak. It is unable to resist enough loads, and you just put it there, and then you call dual system, and you get the benefit of using dual systems. So the code wants you to add a real good, strong moment frame. So how can they do this? They said, well, the moment frame that you need to put in a dual system is going to be capable of resisting at least 25%. So let's say that you do the analysis. Let's say that we have 100 kips, right? 100 kips total lateral force. We do our analysis. Brace frame would take, let's say, 90. Moment frame would take maybe 10 kips. So what do you need to do? Instead of designing it for 10 kips, you design it for 25% of the 100 kips, for 25 kips. So instead of having your moment frame to be designed for 10 kips, you're going to be designing it now for 25 kips, just to make it a little bit stronger. So the code here again wants to be sure that you're going to be using a strong moment frame and not a very weak moment frame.
So we got to design the stiff member for 75% of the strength.
No, you design for 90%.
Okay.
I mean, for whatever it's going to take based on the stiffness analysis. So this is a very good question. So if you have here Does it mean if I'm designing the mount frame for 25%, does it mean that can be taken the remainder of the force to be designed for by the brace frame? I'm gonna say no. The brace frame is gonna be designed for whatever it takes in reality. If you do here stiffness analysis. Don't forget that after you beef up the column of the mount frame and the beam of the mount frame, if you put it back again in the same model, you're gonna see maybe 90% of the forces still goes to the brace frame. So in reality, the brace frame is gonna see most of the load. But the code wants to have a good mount frame in the system. It does mean that the mount frame is gonna be taking this load, but it is gonna be designed for this load. In reality, the mount frame itself is not gonna be seeing 25 kips, it's gonna see maybe just 10 kips or 11 kips. I'm just using your kips instead of percentage, but you guys, you understand, it's gonna be percentage. I have another dual system. It's gonna be intermediate mount frame, which is gonna be a complete different story. Cable resisting at least 25% of the seismic forces, and then you add to it. Still a special concentric frame. Look what happened here. Now it becomes 6. I'm gonna go back here to category D. It's gonna be 8. So once you go here to intermediate, you're gonna be going down a little bit with the R factor, which means total size of design force is gonna be going up. Instead of dividing it by 8, now we divide here by 6. All right. Let me switch to the next slide set. All right. Now we need to work a little bit with SD1 and SDS. I know in your project that you have the same thing, that you need to figure out SDS and SD1, and you should be able to do it. Do you guys have the link to find out SD1 and SDS?
ATC, right?
Yeah, okay, very good. And you guys know that when you do it, you need to use site classes, gonna be D, default D, not just D. Use D default. Difference is gonna be in some factors that I can address while we're talking here. If you like to use it D, it's gonna be fine, but I would rather just use default D so that you guys are trained and you understand the difference between the two. Anyone has a question about the difference between site class D and D default?
Aren't they pretty similar? Between like the factors and all.
No. Now in the new code is a little bit different. Okay, I'm gonna go through it. I'm gonna be sure that I address it a little bit.
Okay, thank you.
No problem. So first, you go to your, I'm gonna say here maps. You go to seismic maps, but nowadays we don't do actually the maps. What we do, we just go online and then you just find out S1 and SS. And once you find here out SS and S1, you need to find out SDS and SD1. So SDS and SD1 is going to be the two seismic parameters that you need to use in your design, not the S1 and S, the short and the 1 second. Now you'd like to figure out the size design category. And the importance of this, I'm going to take you back here. If you go to the previous slide set, do you guys see slide set 9 or 10 now?
Still showing 10.
Okay. Now it should choose 9, right? So as you see here, size design category is really important, right? Because the height limitation is going to be based on the size design category. So I really need to know the size design category. Size design category in the past, They used to call it like high seismicity, low seismicity, moderate seismicity. In the very old code, we used to have the seismic zone 3, 4, 2, and 1. I don't know if you guys are aware of this code gap. We used to have seismic zone 4, seismic zone 3. We used to have 2 and 2A and stuff like this. Not anymore. Now we have the seismic zone category. It goes from B to F. So most likely, once you go here to D or E or F, it means that you're on high seismic zone. How do you figure out if this is going to be high seismic zone or not? I'm going to take you here to chapter 10. So to figure this out, you need to have the risk category, an S1, and SS. So the first test that you need to do here, if S1 is going to be more than 0.75 or equal to 0.75, you go through here, you go through this. If your risk category, let's say 2, you're going to be seismic design category E, which means very high. Meaning that this is going to be very dangerous. If you have an S1 more than 0.75 G, this means that you have real high seismic zone. So this is going to be the first check. So we're going to do it here in order. This is going to be the first check. Once you get it to be E or F, you're done. If it is E here, no other checks are needed because E is like the highest, E and F. But if you do not qualify for this one, which means your S1 is going to be lower than 0.75 G, what you need to do is to go to the next table. Based on this, SDS now is going to be based on the SDS. Look at the SDS value. Look, where are you at? Your SDS is less than this value, or it's going to be between these two values, or between these two values, or it's going to be more than half a G. Look at the risk category. With that, you can figure out your site design category through this matrix. Say, okay, good. Is this the only table? We can say no. Decide on whatever size design category based on SDS. Repeat the same thing with the SD1. In some cases, you do it with the SDS. Let's say that you get B. Now we do it with the SD1, you get C. Now which one is going to be controlling? It's going to be C. So you have here 2 tests or 2 checks. You do the SDS and the SD1. And the one that's going to give you the higher size design category, just go ahead and use it. So if one of them, let's say if the SDS is going to give you a D, and then you try it with the SD1 give you C, it means that you're going to be at D level. This is going to be your size design category. I have an example. They said that we have elementary school, 3 people with the following given information. Here is SD1, SDS, and S1. It says determine the risk category and the importance factor. And then next to that says determine size design category SDC. The risk category here, since you have a school, 300 people, this is a real school, right? Elementary school. It's going to be size design category 3, importance factors going to be 1/4 from the table. We have this table that we went through. Now, I understand that if you're going to be at 0.75 and you're going to be a risk category 3, let me take you back here. Okay. I'm going to be 0.75 risk category 3. I'm going to be size design category of E. So I have it from this table. Once I do this, I don't really need to do these 2 checks for SD1 and SDS. So if S1 is more than 0.75, you're done. You can just move forward. So now here's your size design category. The SDC, right, is going to be E. Second example, it says a factory produces hazardous materials that may affect the public. What does it mean? Is this seismic? Is this risk category 2 or 3 or 4? Say hazardous materials. Any idea?
Risk category 3.
3. They give me the location. So with this location here, what I did, I went to the website. I was able to find out SS and S1, the 2 values. Nowadays, with the website, once you key in both of these 2 pieces of information, You get right away all the values. I'm sure that you guys have seen it before. Would anyone needs help with the link to that website, or are you guys good with it?
What's the website again? The link? You just
Okay. Give me a second. You see it in the chat? I just sent it in the chat. And what you can do here, you can go to SIAC or ASHPAD, or you can go to the ATC. What you need to do is just to input the coordinates, like these two coordinates, latitude and longitude. So when you key it in the website, put as -117. Be sure that you put the negative sign. Now, the way this works here, after you find SS and S1, you need to look at the two tables. What two tables? I'm going to say these two tables, you know. We have more tables for FA and FV. Let's hope that I have it here. Oh, I don't have it here. Are you guys familiar with the FA and FV tables, or should I show it to you? Yes? No?
Can you show them to us, please?
Sure. Here's a table for FA. Have you guys seen this before? Maybe most of you guys have seen it. Okay. So based on the site class, so we have D and then we have D default. You see this F, and then it says here E, and then at a certain point, you don't know exactly what's happening, right? It says here C section, C section, C section. So what's going on? Not clear yet. So FA is right there, right? You have here FA for site class D. It's going to be based on the SS value. So based on the SS value and the site class, you can figure out this factor FA. Do the same thing. Just do it here. You say, okay, here's F sub V. It's going to be based again on the site class and this S1 value and this S1 value. Based on this, you find out F sub V. So what is this A here? What is this section 1148? This section here, it says, if you don't have enough analysis when it comes to site class D, right? See, this happens in D. If you don't have enough analysis, and this is happening usually by the soil engineer, geotechnical engineer, it's not by you as structural engineer. If you don't have enough information about it, on this, you're going to be using a little bit different factors. So if this going to be site class D, use these factors. But if you don't have enough analysis, we're going to call it D default. When it comes to D default, your factor here is going to be at least 1.2. And we're going to go through this. This factor here is going to be 1.2. 1.2. It's not going to be 1.0. And this in section 1148. If you guys are not familiar with this, this is really important, which is this part here. So let me go back here to our slide set. So once you take these two factors, you go to the tables, and in this case, it was treated as site class D, not D default. I was able here to find out FA and FV from the two tables. Now the SMS and SM1, what you need to do is just take FA multiplied by SS for the short period and FV for the velocity multiplied by the long period, the 1 second. And the final design value, you're going to be taking these two values, SMS and SM1 multiplied by 2/3. You're going to reduce it a little bit. And this is going to be the two factors that you need to use in your design, SDS and SD1. And these two parameters would be used into our equations, the design force, size design forces. How can you find out the size design category here in this case? Size design category, I'm going to say, as we said, first we're going to do this check. If S1 is giving more than 0.75, we're going to do the single check. If not, we're going to be doing here two checks, which is this one and that one. So let's look at this. Now, S1 is not more than 0.75 G. So we failed this check. Second check. I have here SDS, let's say 0.29, and SD1, 0.17. So 0.29 and 0.17. .29, we're going to be here. Risk category, what is the risk category again?
3.
3, which means we're going to be size design category, size design category B. The next one is going to be 0.17. So I'm going to go here 0.17. We're going to be in here in this category. This category 3, it means it's going to be C. So when we did the first test, it was B. Second test, it is C. So this is exactly what we have here. The first test is going to get you B. The second test is going to get you C. Your final size design category is going to be C. I give you here kind of two tables. It should make your life a little bit easier. And here's what you need to do. You look here at the SC value, SS value. Look at the SS value, and let's say it's going to be 0.3, right? Because the one we have here is 0.289. So it's going to be very close from 0.3. Look at the site class. If your site class is going to be D, this is going to be the value of your SDS. So this value here is going to be your SDS, which means this table here includes the FA and FV factor, and also includes the 2/3. So once you have here the site class, you don't really need to find the FA and FV. You can just use this table. And with this table, you're going to find out the SDS. Same thing. Here's the table for the SD1. If your S1, for example, is going to be 0.1, you go here to D, your SD1 is going to be equal to 0.16. Next to this, I see here stuff. It says something slash something, B slash C. What does it mean by that? D, this gives you the size design category. So instead of doing these checks with the tables, right, we should be able to use this modified tables and find out the size design category. But I'm trying to find out what does it mean by this D only, D. Okay, this makes sense. If the SS value, let's say, is going to be 0.7, and you have here seismic, you have site class D, it means that your size design category is going to be D. This is easy. But the problem is when it comes to B slash C or C slash D, what does it mean by that? To know what does it mean by that, what I want you to do is just look at this key right here at this location. If it just says A in the table, it means it's going to be A for all risk categories. But if it says, let's say B slash C, it means for risk category 1, 2, and 3, it's going to be B. Risk category 4 is gonna be C. Okay, let me try to understand this here. So your SDS, your SS is 0.3. I'm just making up here a problem. So you can see here, my SS is equal to 0.3. I have side class. I'm gonna put it here as, let's say C. All right, I decided to make it C, a little bit different. What else? I'm gonna say the use of this structure here, I'm gonna say it is gonna be essential facility. What's essential facility? Like emergency facility. What does it mean by that? I'm gonna have here seismic, it is gonna be risk category what, 4? Is it 4?
Yes.
It is gonna be 4. So based on this information here, what seismic design category would you have? You can see here, SS is gonna be 0.3. Yeah, I'm here. Site class is gonna be C. So the SDS is gonna be 0.24.
See?
And then yes, it's gonna be C. Why? Because this is gonna be reserved here for risk category 4, and B is gonna be reserved for risk category 1, 2, and 3. So I'm gonna say here SDC is gonna be equal to, then I'm gonna put here C. This is correct. All right. So this table should save some time or some headache, I guess. If you are unable here to use your computer. Now the natural period. How do we figure out the natural period? I have here multi-degree freedom system. It's gonna be 2-degree freedom system. A moon frame. Not sure about the column section or the size of the column and the size of the beam. I don't have it. Not clear to me. I have the location. And I'm trying to find out what natural period to use if I'm going to be doing here the code analysis. The weight that the top beam is going to be supporting is 1200 kips. The bottom beam at the second floor is going to be 1000 kips. The story height for each one of them is going to be 15 feet, and then 15 feet total of 30 feet. I don't know the span of the beam. I don't really need it. I did some analysis on this moment train. When I applied here 200 kips and applied here 150 kips, displacement due to this static force is equal to 1 inch here, and here's going to be 0.35 inch. Total displacement of the second floor, total displacement of the roof. The question is, when I use here the code equations, what natural period should I use? So first, I need to do the accurate, and then second, I need to do the approximate natural period, and then do the comparison and find out C sub U. This is going to be the practice or the exercise I need to do here. I'm going to do here the accurate method to determine here the natural period. So I have good example. I have all numeric values. So it says here 2 pi square root summation of from I to n, number of stories, right? I have 2 stories on. If I have 10 stories, I still can use the same equation. That's going to be from 1 to 10. Wi is going to be the weight supported by the top beam, is going to be 1200 kips times the displacement, delta sub I, which is this delta S in this picture, 1 inch square, plus the lower level is going to be 1000 kip multiplied by 0.35 inch square. So I get to be careful here, units. I'm going to be using here kips and inches. So for the weight and the force is going to be kips. For displacement and dimension is going to be in inches. Divided by, now I said inch. So G in this case is going to be 386 inch per second square. Multiplied by summation of F sub I delta sub I. What is F sub I? This force multiplied by this delta. So it's going to be this force here, 200 kips multiplied by an inch, 200 by 1 inch, 150 by 0.35 inch. Based on this, my accurate or exact natural period is going to be 0.73 seconds. This is going to be the exact natural period. But this is not the one that you can use in your equations because you did not do check yet against the code maximum natural period to be used. You're gonna see here now, let me try here the approximate method. I have a steel seismic moment frame. Here's the C sub T and the X component. Where is this exponent coming from? I'm gonna say from the table. We went through this already. So T approximate is gonna be equal to 0.028 times 30. What is the 30? The height of the building. If you look here, total height of the building with the moment frame is gonna be 30 feet to the 0.8. It's gonna be 0.425 seconds. Now, should I compare the 0.73 directly to the 0.425? I'm gonna say no, I need to find out also C sub U. How do you find out C sub U? Oh, I need to find it from this chart, right? You're gonna say this is gonna be the one that goes 1.4 or 1.7, or you can do interpolation between the two. It's gonna be based on the SD1 value. So let's say I'm here, I'm able to find out the SD1 is gonna be almost 0.4 seconds. It means in this case, the C sub U is gonna be 1.4. The maximum natural period that you can use in the code equations is going to be equal to C sub U, the 1.4 multiplied the 0.425. It's going to be 0.6 seconds. So when I did here the dynamic analysis, I was able to get to 0.73 seconds. My max is going to be 0.6. Which value can I use? It's going to be the 0.6 seconds. And here we go. Here's a 0.6 seconds. Any questions? All right. Another moment frame here. I have the location 40 and negative 118. It's supporting 1,000 kips, and they have 6 moment frames. It says here that you have 6 typical moment frames in each direction of the building. And it says, what is the design or how much is the code design page here? I mean, you just ask here to solve for it. You have the column size, and this column is fixed because it's going to be fixed at the bottom. And we assume it's going to be fixed to the diaphragm. It has to be fixed for a moment frame. We have this total load supported by 6 moment frames, which means by 12 columns, because 6 times 2 is going to be 12 columns. You have the moment of inertia of this column. And in order for you to find out the design forces, size of design forces, you need to find out the inertial period, T, of the building. And this is the reason that we have the column size, we have the weight. So first, since I have the coordinates, I'm going to be able to do the SD1 and SDS. So I'm going to jump right here. Now I don't need to go through this. Here's the SDS and SD1. Natural period of the building, this is now single degree freedom system. I understand that you have lots of columns, but they have only one direction of motion. It is not like 2 levels. So I'm going to say natural period T is going to be equal to 2 pi square root of the mass divided by K. The stiffness here is going to be equal to 12 EI over H cubed because I have fixed case. If I have fixed hinge, it would have been 3 EI divided by H cubed. So I have here 12 because I have 12, right? 12 EI, 12 times E, 29,000 KSI. So I'm using here kips and inches. So be careful about units. For the moment of inertia, I have 12 columns times the moment of inertia for this column here, the W14 by 211. So this 12 here, because I have 12 columns, this 12 here, this is a constant in the equation, divided by the height cubed. The height here is going to be 15 feet. Look at this height, 15 feet, times 12, because I need to put it in inches. As I said, be careful about units here, cubed. Now the stiffness is going to be this much kip per inch. So my units here is going to be kip in inches. Now my natural period equation is going to be 2 pi square root of 1,000, which is the weight divided by G. So this value here is actually the G value. 386.4 inch per second square. Divided by the stiffness, 1904.7 kip per inch for all columns. And with that, the natural period is equal to 0.23 seconds. So this natural period here is going to be based on dynamic properties. I don't have the approximate value yet, and I need to find it out. Now here's a hypothetical question. What happens if the exact natural period is lower than TA? Let's say TA is going to be 0.7 seconds, right? And T, the accurate method, gives you here 0.23. Which one to use? If you have a really stiff building, let me put this assumption, just an assumption. T accurate equals, we can say here, let's say 0.4 seconds. T exact, which is accurate based on this analysis, let's say 0.2 seconds. C sub U equals 1.4. What natural period do you guys want to use in your code equations?
0.4.
Is going to be 0.2?
Yeah, because the T max will be much larger than the
Tmax.
T.
Let's find out T of Tmax. Tmax is going to be C sub U times TA. Is going to be 1.4 times 0.4. How much is that? Can someone help me?
0.56.
0.56 seconds. This is going to be the max. Now, which value should I use in my analysis?
Bigger value.
Code says if you have means or methods to do the accurate method, which means this one here, do you see this T? Do it. And compare it with the maximum natural period. So now my dynamic natural period is 0.2. It's right here. The max is right here. Should I use this or should I use this? The max or the actual value? You can say, if the accurate method here is going to give me a natural period lower than the max, of course I'm going to be using this. So actually the answer is going to be, this is going to be the answer. This is a value that you need to use. So unfortunately, your seismic force is going to be slightly higher than what you'd like to see. So someone's going to say, if this is the case, why would bother and just do here the dynamic analysis? Let me just use TA. Well, it's going to be up to you in this case. Are you guys following me here? Any questions on that? Okay. Now let me try it here to find out the approximate method, find out TA. I have here the CT and X exponent. TA now becomes 0.244. C sub U with this interpolation is equal to 1.5. T max is 0.38 seconds. Now I'm going to compare 0.23, which is this natural period, to 0.38. Of course, it's going to be lower than 0.38. I'm going to be going ahead and use the 0.23. For this moment frame, the R factor is going to be equal to 8. This special moment frame, your R factor is 8. And here are the code equations. I'm going to be using them all. You have CS, CS max, minimum. Here's the total shear force applied on all the moment frames. 81 kips on 12. Is it 12 moment frames? 6 moment frames, 12 columns. You have here this 81 kips. So I hope by this example that I'm clear on exactly what we need to do to determine the seismic forces on a moment frame. And the big question is, how can you use this, right, when it comes to your project? So, okay. Vertical distribution of seismic forces. I guess this is going to be important. right? Because we're gonna have here 3-story monoframe. The force that I was able to find out here, this 81 kips is gonna be applied here on 12 columns. But this is here 1 story. The problem is gonna happen when you have, let's say, 2-story building or 3-story building. We have an equation here with the code, right? This equation. The equation says total force acting on the building, we're gonna call it V. Fx is gonna be the story force. This is gonna be the applied force at each level. So it's gonna be equal to coefficient, it's gonna be called CVX. What is the CVX? Coefficient, seismic coefficient. X is gonna be for the story, and V because is gonna be about the seismic force for the base shear V. And look at this equation here. It says Wx, which means the story level, times H, which is the height of the story measured from the seismic base, to the power of K, divided by summation of from I equals 1 to N, all the stories, Wi times Hi to the K. This K is going to be based on the natural period, this exponent here. Have you guys done this before in any class? This vertical distribution? Okay. So I gave here an example. It shows here 10-story, excuse me, 10-story building. And you give here natural period. With the natural period, you can figure out the K factor. They give you here the weight for each level, and the total seismic force base shear is equal to 800 kips, which is just happen to be the same. And the story height is going to be 10 feet. So the question is about this HI. What is this HX and what is this HI? So this HI is actually the elevation of each one of these levels. So in the first level is going to be at 10. Second is going to be at 20, 30, 40, because the story height is only equal to 10 feet. This example should be very simple, right? Because here I have the weight for each level, HI and WI times HI, like what I have here in this denominator. You add them all up together with this number here, 1252, which is going to be this number. Now you take each one of these levels, Wx times Hx to the power of K, which means one of these values, divided by the total, and this gives you your CVX. Take this number here, multiply by the base shear, the 800 kips. It just happened to be the same, right? Just give you seismic force in each level. If your K is equal to 1, I should expect distribution is going to be similar to this triangular distribution. I'm going to put it right here, if this makes sense to you guys. So let's say here's the building. So if your K is going to be equal to 1, and this K is going to be equal to 1 when natural period is going to be real low. Because look at this. When natural period is going to be less than or equal to half a second, your K is going to be equal to 1. In a case like this, the value of the forces on each one of this level, the story forces, is going to be kind of following this distribution. Meaning, let's say that I have 3 stories, right? Let's say I have only 3 stories. If I have 3 stories, here's the top one, middle one, and the bottom level. So let's say that I have here 3 stories. The first force is going to be applied here is going to be F. The second one, which is applied in the middle level, is going to be equal to 2F. 2 times F. And the one on the top level is going to be equal to 3 times F. So someone's going to say, if the total force applied, if total force, on how many levels again? I have only 3 levels. So let me extend this here. Equals, I'm going to make it here 600 kips. Just make it up, okay? Total force is equal to 600 kips. The total force, according to this distribution here, is going to be equal to 6 times F, right? You have 3 plus 2 plus 1. meaning is going to be equal to 6 times F. Therefore, F equals 100 kips, correct? What does it mean? It means that the force acting right here, this force, which I put it to be equals to F, right? This is going to be equal to 100 kips. And this force, 200 kips. And this force, 300 kips. Total of 600. So distribution is going to be triangular shape distribution as long as you have low Nash period. And once Nash period is going to be going higher, this number here is going to be shooting up, and the middle numbers is going to be coming down. So distribution is instead of having this triangular shape like a straight line, when the Nash period is going to be low, it's going to look like this. The top value, which means the roof forces, is going to be going higher than that for the triangular distribution, the straight line, and the middle lines or the middle levels is going to be coming smaller. This is going to be the standard distribution when Nash period is going to be going up, and this is going to be the standard distribution when you have low Nash period of 0.5 or less. Now, seismic provisions. This is going to be the 341.16. Did you guys download this already? It's free download. Did you guys do it, or do you need the link?
Yeah. Please send the link.
What?
Please send the link.
Okay. Let me know if you have seen it in the chat. Is it there?
Yeah.
Excellent. Very good. All right, we have chapters. I really care about the general provisions and the general design requirements. This is getting really important. 3 chapters, right? And then the analysis. What type of analysis you can do, what you cannot do, and this type of things. Member and connection requirements. I guess this is getting important, right? So what's next? Moment frame system. If you like to do a moment frame design, you need these chapters. Why? Because the first 4 chapters is going to be important for any seismic design. You need to understand all of that. If you are doing here moment frame design, go and read chapter E. Looking for a brace frame and shear wall system, steel shear wall system, you're going to go to F. Composite moment frame is going to be G. Composite brace frame is going to be H. So I guess we now know where to find our information. This give you like the main chapters that you have in the 341 2016. What is the general design requirements? And which code do you think we need to use? The design code for us is going to be the CBC. When we come to design forces, it says, take this document EGCE530 and use it in your analysis. So this is going to be the one that we need to use. So this design base shear that we have used is going to be based on the ASC, which is also based on the CBC. So all of the design requirements, which means design code requirements, right? Design forces, displacement, and so forth, is going to be all based on the CBC and the ASC7. How about the drift? The drift, after you're done with your analysis, now you can have the deflection, and once you have deflection, you're going to multiply by C sub D. What's C sub D? I'm going to say this C sub D is taken from this table 12:1 that have the R factor, which is the same as ductility factor. So, okay. How about the load combinations? Where did you get taken from? I'm going to say load combinations, I guess they are also in the CBC. We went through them before, right? Now we are going to have seismic forces that you need to include. And in many cases, you're going to see here a combination of seismic force and dead load. And then in some other cases, you're going to see here the term EH and EV. EH means horizontal force, seismic forces, and EV is given vertical seismic forces. Excuse me, let me close this. Yeah. So what is EV and EH? EV is given the vertical seismic component, and EH is given the horizontal seismic component. The equation, when it says here V equals CS times W, this is actually only the EH. Now, there's something called overtrans factor, which means the maximum design seismic force that the structure is going to be able to see, or certain members going to be able to see. This is what we call here EMH. So E stands for the seismic force, whether it's going to be axial force, moment, shear, just E. When it says EH, it means horizontal. When it says EV, it means vertical. When it says here EMH, it means it's going to be maximum horizontal force for certain connections or members or whatever. How do you find out EMH? You take EH, which means the seismic force, based on the V, which means a phase shear, multiplied by this omega naught. Where do you get the omega naught from? The same table that has the R factor omega naught that C sub B. So all of that is going to be based on the CBC. If you look here at this, my red marks here, it says CBC and ASCE. So general design requirements, design forces, design displacements, load combinations, this is going to be all based on the CBC and ASCE 716. So what's the required strength? The required strength is going to be based on what? It's going to be based on the structure analysis. Now you're going to have the V, which means a phase shear applied on the structure. You're going to be taking it, distributed on the bracing members, and then applied on the structure. Now, between a lateral resisting system like moment frame, or a brace moment frame, or a brace frame, you can have different design forces for different elements. This is why it says here you go to chapter D, E, F, and G, and H, because start from chapter E here, you're going to be looking at certain frame system or brace system that you need maybe to change the design loads accordingly. The other question is now, what is the available strength? Available strength means the capacity. We call it here PRN. What is PRN? PRN, it could be PMN, which means the flexural capacity. It could be PPN, axial capacity. It could be PVN, which is the shear capacity. All of that, for now, we just call it PRN. Is going to be like the general term for it. This, if you are doing LRFD design, which we are going to be doing. If you are doing ASD, you're going to be taking RN, which in this case is going to be MN, PN, or VN divided by this omega. This omega depends. It's 2.5, 2, 3, depends on which member that you're designing or which force that you're designing for. The system type here, as we say, is going to be based on the chapter. The first 4 chapters is going to be kind of general. The following 3 chapters is going to be based on the structure system that you're trying to design. I'm going to take you back here to this slide set. First 4 chapters is going to be general. After that, if you're interested in the moment frame, you go to chapter E and so forth. And this is indicated here in the system type. As you see here, these are sections of chapter B. It says here B1 means chapter B, section 1, B2, and so forth. Now in chapter 1, it says here some general requirements. The materials as a steel here. There's something very important that you need to understand. The material strength is usually, we refer to F sub Y and F sub U, which means yield strength and ultimate strength. But in reality, if you like to take a sample and test it, this material is going to give you higher forces. So we call this the expected material strength. If I said here 50 KSI, it doesn't mean that the test value is going to be 50 KSI. Most likely it's going to be higher. And the question is higher by how much, right? And if you say here F sub U is going to be higher than 65 by how much? It's going to be higher by this given factor. Look at this factor here, R sub Y times F sub Y. And this factor, we're going to have tables for it. Same thing for the maximum strength, ultimate strength. So F sub U is going to be R sub, if you like here to look at this, R sub T times F sub U. And this is going to be the expected values, meaning we're not going to be just using F sub Y and F sub U. We're going to multiply by some factors because we know that the actual strength is going to be slightly higher than the specified strength. I'm going to stop at this point here, and you guys let me know if you have questions. Otherwise, I'm going to see you next time in class.
You mentioned earlier about EV, earthquake vertical force.
Yeah.
When do you have a vertical like force, due to earthquakes?
All members, all buildings. You need to design for E sub V.
Okay.
And the equal, it's simple. The equation for it is simple. It's going to be 0.2 SDS times the weight.
Okay. Okay.
Yeah.
Because I'm just thinking like earthquake hits laterally, so.
No, you have also vertical component. Give me a second. EV. It's called EV. Give me a second. You see my screen now, I guess. Let me show you this. Here's a code equation. I'm sure that you have seen this before, right? You see this E is equal to EH plus EV. So EV is going to be the vertical component. So actually, when just it says E, like in the code, right, it should be the effect of EH plus EV. EH is going to be horizontal force, and EV is going to be the vertical force. You see here this equation for EV. I want to find out this EV for you. Here's EV. You see it here? 20% of STS times the dead weight. In the design of a mount frame, steel mount frame is not that critical. In the design of a cantilever beam, is going to be very critical, or cantilever slab, because it is added to the dead load. They say that you have concrete slab, a cantilever is going to be very important. If you are doing a design of a shear wall, it's not really critical. It's not going to be changing your design that much, If you design here a mount frame, it's not going to be that critical. So lots of people just ignore it in their answers, but it's important. It's an important component that you should not ignore it. And as it says here, vertical seismic load effect. All right?
Thank you.
No problem. Right. Right,
Is
guys.
there any homework due this week?
It's going to be about the project. I'm going to be just doing a little bit of the project. I'm going to ask you to start to work on the seismic analysis for it, and that's it.
Okay.
All right. So I'm going to assign it. You can do the SDS, do the SD1, this kind of work.
Thanks, Professor.
Great. Thank you.
All right.